I have a question. Where did this negative come from right here when I did the derivative? Where did that negative come from? What's the derivative of sine of 2x? What do you have to do? Kick out the 2 when there's a number multiplied by the x. Is there a number multiplied by the x here? Negative 1 is multiplied by that x. So when you bring the 1/2 down in front, drop that to a negative 1/2, you have to kick out a negative 1. So the y prime, so this is our t chart. Here's our differential equation. Now I think I mentioned this to you yesterday, right? That the y is on the bottom on number 6. Didn't I say that before you guys left the room? Okay. So they give you the proposed solution. They say, hey, we think y equals square root c minus x is a solution to this. So I wrote it to the 1/2 power, brought that down in front, and then so I substituted that over here for my y prime. And then for y right here, I substituted in the y. Well, square root of that's the same as 1/2, so it looks like this. Now I don't want to stop here because I want even a third grader to know that these are equal. And you know, if you look at this and this, those don't look equal because of that negative power. So you need to flip that to the bottom, write it like this, and then you can show, okay, hey, those two are equal. Now part B said they think that negative square root of x is also a solution. I'm not going to work through it, but let's look at what would happen. If there was a negative here, when you bring the 1/2 down in front, that would be negative, but then when you kick out the negative 1, it would turn positive. So this would all be positive over here. And on this side, you would have a negative square root here. So you'd have a negative on the bottom and on the top, and that would cancel, and so it would turn positive. So therefore, the two would be equal as well. So therefore, square root and negative square root are both solutions, okay, by doing that kind of that T-chart method of showing that those that works, that the two sides are equal when you make the substitution. All right. Now, had the question come up, so it'd be worth talking about real quick. What was number 20? Number 20 said y equals t squared over 2. Is that right? And then over here it had y prime equals y, right? And so that's kind of backwards from where we want. Sometimes it's confusing. Where does this t chart, where do I put the t chart? Which one of these two do I draw the line on? This one, right? Because 50-50 chance. You got to think of it like that 7th grade example I gave you. X equals 4 is the solution. That's what we plug into the equation. So which one of these is the solution? The left one, right? The y equals. Remember what we said. A differential equation is an equation that contains derivatives. And the solution to a differential equation is what? The original function y, or whatever the function name is. The original function is your solution. So that's why you know this is the solution, because it's y equals. So the solution gets plugged into the equation. So the t is over here. Okay, so now, here's another thing I was helping somebody with this morning. Whenever you see this, well, of course, this is going to get plugged in over here, so t squared over 2. But whenever you were going to do the derivative of something that has division, division is our enemy. I hate division. I hate subtraction. I would rather, matter of fact, I always tell my algebra class, we could take the division key and the subtraction key and just break them right off the calculator, but I quit doing that because with that class, some of them just they will actually break it off my calculator, so I quit telling them. But you don't need them, because division is the same as multiply, subtraction is the same as add, right? As long as you do the opposite or the reciprocal, that kind of thing. Division really screws us up when it comes to doing derivatives. There's a special rule we'll have for division, so sometimes we have to think about division. And we'll have a special rule for that. But we don't have to use it here. What we should do instead is we should rewrite this as 1/2 t squared. So you're always going to see me working with fractions, not division. It just makes things easier. So now when we do the derivative here, we bring the 2 down in front. That makes 1. T to the first. It's just that. So we come over here, and in place of y prime, we put t. We can tell those two are not the same. So this is not a solution. Okay, so just a couple of little tips there to help you with equations like that. Where do you put the t and which one does it go? It goes in the differential equation, and then your solution is the y equals, and that's the thing that gets plugged in. And that's where you do your y prime, and so you can plug it in. Okay? All right. Anything else on that section? Was that the one that had the average velocity problem, or was that the next section? That was the next section. Okay, let's go to that. So on 30, was that 37? Okay, let's talk about 37, because I know it's an odd one, and you could just look in the back of the book, but you shouldn't be satisfied with that if it doesn't make sense to you. All right? They said x of t is a position function. It's ln t, and it's in meters. So this is like a distance, position. All right? They want the average velocity. And so people have been asking me, well, what's that mean? Well, it doesn't mean add up and divide by 2. In this class, I can't even think of a time, I hate to say never, but I can't think of a time in this class when we're doing an average where we will add up and divide by how many are there. That's not what we do. It has to do with average rate of change versus instantaneous rate of change. Remember, we've put those two up there. What's average rate of change? Slope between 2 points. That's average rate of change. It's an algebra 1 idea. What's instantaneous rate of change? Slope at 1 point. What's the name we have for slope at 1 point? Starts with a D. Rhymes with derivative. Derivative, right? Right? That's instantaneous rate of change. Well, you come up with something that rhymes with derivative. Laugh at me. All right. So average rate of change is slope between two points. And they give you the 2 points, 1 and E. Right? So we plug E in. We plug 1 in. That's it. That's average velocity, because velocity is meters per second. That's the derivative. That's the rate of change of position. So average, anything in this class usually means average rate of change, and we do something like this. So this is easy. We plug an E into X. We get ln E minus ln 1 over E minus 1. ln E, of course, is 1. ln 1 is 0. We get 1 over E minus 1. This would be a no calculator. I mean, we should do all these like they're no calculator, and then if we need a calculator, that's easy. We just type it in. But basically, that is average rate of change. Okay? The reason you can't do the velocity, like for example, what we had talked about was you could do velocity is a derivative, right? If you understood that, you could say, oh, I can do the derivative, do the velocity of 1, do the velocity of E, and average it. Now, if you've been in physics, you probably have that equation. Isn't there 1 v sub I plus v sub f divided by 2? Right? Isn't that an equation? Isn't that a thing? Average velocity, initial velocity plus final velocity divided by 2. That only works if constant acceleration. That only works if you have constant acceleration. You can add the initial and the final velocity and divide by 2 and average it. But we don't have that here. This isn't constant acceleration, okay? And so it doesn't work to do that. All right, B, instantaneous. So what's instantaneous rate of change? The derivative, x prime. So we do the derivative. Derivative of ln t is 1 over t. So then we plug in an E, and we get 1 over E. Right? We want the rate of change at E, and that's derivative. So again, average rate of change versus instantaneous rate of change. Slope between 2 points, and then slope at 1 point is now derivative. Now what we used to do is pick 2 really close points. Remember that? We picked 2 really close points, but that was before we knew our shortcuts. That was before the definition of the derivative. Right? We picked 2 really close points to get the slope at 1 point. Well, now we can get the slope at 1 point by doing the derivative. We do the derivative, plug in our point, we got it. We got it. All right. Let's go on to, I want to do number 44 in the other section with the calculator. Is there any other ones you want to see? 39 in that other section as well? And that's the no calculator one. Okay, here's what I'm going to say about that. And because I do want to give you some work time today, a fair amount, and so if there's some things I don't work through with you today, you can ask me about them when we have some work time here. But if we go back to yesterday, number 37. So let's talk about this max-min stuff. So that was our differential equation stuff. Don't really have too much new to add to the idea of different. Oh, wait a minute. There was another one there, I thought. 47, 48, 40. 43, that's the one. Thank you. 43, we do need to talk about that. So I don't want to leave differential equations just quite yet. But let me finish my thought on the local max min. So yesterday we did this. We did number 37. Okay? And so and 39's like it. So you do the derivative, you set it equal to 0. Now I will say one thing about 39. Instead of 1/2 plus cosine, it came out to be 3/2 plus cosine, right? And when you subtract 3/2, you get cosine equals -3/2. When's that happen? And never. Cosine's never equal to -3/2. So that means there's no stationary point, right? The derivative's never 0. So what are your candidates? Just the endpoints. So you plug in the two endpoints into the original, and there's your maximum. But now let's think about this for a second. If a function never has stationary points, what's that mean? It's what? It's got to always be going up or always going down. It can't turn around. If it turns around, it's got to have a slope of 0. Unless it did something weird like a sharp point or something, but we're not doing that right now. So it's always going up and always going down. Now picture that. Picture a graph that's always going up. Where's its highest point? Well, but we're only going from 0 to 2 pi. So it's going to be at the right edge, right? If it's always going up, the highest point's at the right edge, at 2 pi. And the lowest point's going to be at 0. It's got to be, right? And then vice versa if it's always going down. So it's going to be at the end point, right? So that's a little bit of what's going on in 39. Now, I will say I did not do all of 37. I don't know if you carefully looked at the directions on 39. You may not have, because I told you 39 was going to be just like 37 that we did. I only did one part of 37. I did the global max min. It also asked for the local max min, and it asked for the inflection point. Now, if you didn't do that on 39, that's okay, because you're going to do another one like it for tomorrow, and then, or for Monday, and then you can do all of that for that. Okay? But what would we do to do local max min and then inflection points? Second derivative, and we would do not list of candidates, but number line. Number line. Now, we're going to review that here in a second, that idea in a second. But I do want to go back and do that number 43. Yeah, number 47 or 48, that was the bank one with the interest, and you just had to do the AE to the KT, plug those numbers in, okay? And again, we're going to have some work time today, so if you've got some questions on those, I'd be glad to help you on those and talk to you about those. But let's look at the one on page, you said that was 43, section 2.5. Okay, so here we go. I would like everybody to turn back, or turn to page 128, if you would. Turn to page 128. And there's a box there on page 128 that I want us to look at. Now, one of the things I want you to do on our next quiz is be able to translate English language into differential equations, into mathematical notation, okay? Because one of the real powerful things about differential equations, this is why it's so important to engineers. One of the powerful things about differential equations is being able to describe real-life situations in a pretty concise way. And so this box has some examples. For example, y prime. So again, when we see y prime, we're going to think rate of change. So y prime equals 0 would be like saying the growth rate is 0, which would be like the position of a fixed object or the value of a no-interest bank deposit, right? There'd be no growth, no change. Y prime equals 0.06y. We said this one yesterday. The growth rate is proportional to y itself. This is like compounded interest. Y prime equals k times t. This is like the growth rate is proportional to t. Notice every time there's a K in there, they say proportional to. This would be like the height of a free-falling object. The rate of change of the height is proportional to time. So as time increases, the height increases or decreases depending on whether it's going up or down. Y double prime is proportional to K, or is equal to K, a constant. Well, that's like constant acceleration. That's also the height of a free-falling object, because its second derivative, its acceleration, is constant because of gravity. And then we get this last one. Well, it turns out this last one is actually the answer to number 43. Y prime is proportional to the difference between Y and 65. And it says Y would be the temperature of a warm object in a 65-degree room. This would be that situation. Well, let's forget that just for a second, and let's look at the words in 43. So what's it say? It says, Allie, read it to me. Okay, stop. So the first part she said there is the rate that an object temperature changes. So right there, that makes us think T prime. I think they told us to call it T. So right there, that makes us think of T prime. The rate. As soon as they use that word, we think derivative. So we write down T prime. Okay, then keep going. Stop. Is proportional to. So as soon as I hear that, is means equals. Proportional to means I put a big old K with a time sign. That's what we want to think of when we hear proportional to. Chances are any problem I give you is going to be worded very similar to this. Okay, go ahead. Proportional to. Okay, so it's proportional to the difference. So the only way I can write a difference then is to put parentheses around it. And it's proportional to, she said, the temperature of the object and its surroundings, S. And in this case, the example we said a minute ago was a 65-degree room. Think about this. Think about this. So if this is 65 right here, the temperature of the surroundings, T is the temperature of a cup of coffee. So we have a cup of coffee sitting here. The cup of coffee has a temperature greater than the room temperature. The room, let's say, is 65. Let's think about this. The rate that the temperature is changing is going to be bigger when this side is bigger. K is a constant, so when this parenthesis is bigger, this will be bigger. So the rate will be bigger when these parentheses are bigger. When is this going to be its biggest? When the coffee is the hottest, right? When the coffee is the hottest, this difference will be the greatest, and then that's when the rate of change. Doesn't make sense. It will cool faster at the beginning, and then as it gets closer to room temperature, it'll slow down. And so this is a pretty easy little equation that describes that situation. The rate of change is proportional to the difference between the temperature itself and the room. Okay? Of course, then the problem is how do we solve that, right? And that's why an engineer would take a course in differential equations to then solve that, because what you really want to know is, okay, that's great. That describes the situation. But I want to know after 5 minutes how hot the coffee is, or after 7 minutes. Or how long will it take the coffee to get down to this temperature, whatever. And I can't do that with that equation, because little t, time, is not even in there. That's one problem with differential equations, is sometimes the input variable isn't even in there. And so I can't solve and I can't work with it. So I need to do the solution to the differential equation so I can then have the original function so I can work with it. That's the idea behind differential equation. So I want you to be able to translate words like that into a differential equation. All right, let's do number 44. This is a calculator, global max min chart kind of thing, and so I want to go through very carefully some stuff you can do on your calculator and what this should look like. Because on this next quiz, a big part of the points is probably going to come from chart, global max min kind of stuff. You're probably going to have one with a calculator, and you're probably going to have one without a calculator. So kind of like 39 was, and then kind of like 44 was. Okay? And so that's going to be a pretty big part of this next quiz. All right, so f of x on 44 is equal to 2 cosine x plus sine 2x. Now, if this is a calculator problem and it's a fairly complicated kind of function, it's probably going to be a trig function. I don't know if I'll do a trig function on both parts of the quiz, but for sure on one. Probably the no calculator for sure, because I want to make sure you can do some unit circle stuff and know some trig stuff. So you're going to need to review that. This is a calculator one. So here's what I would do. So Carly is going to be the demonstrator today. And so I think everybody ought to get out your calculators, and we're going to, here's kind of what I would do. Now, how much of it you use your calculator is kind of up to you. All right. But like we said, there are certain things that have to be shown, right? So what is the first thing asked in number 44? What's it asked for? Okay, so we have an interval 0 to pi, and we want to know if there's any stationary points. So what do we need to do for that? Do the derivative and set it equal to 0. Now, do you want to do it on the calculator or do you want to do it yourself? Either way, I don't care. You're going to have to kick out a 2 when you do the derivative over here. It's probably good practice to do it without the calculator, but let's talk about right now what it would look like on the calculator. So Carly, first thing I'd like you to do is just type in f. You don't have to do this, but I'm going to show you some advantages to having the functions typed into your history area so you can go back and grab them when you want them. So just type in f and hit enter. And so now it's there if I want to go grab it. And I do right now because I want to do the derivative of that. So go to your template, which is next to the 9. We're going to grab the derivative template. And we're going to then go up and arrow up and grab it and hit enter. And now we have f prime in our number line. Now notice it flipped it around, right? It flipped it around from the way she wrote it. When she typed in 2 cosine x plus sine 2x and then she had entered, it flipped it, you know, and then it does a derivative because it has a certain order it likes to write it. So I can always tell on a quiz if it's a calculator one, I can tell if somebody did the derivative themselves by hand or they put it in the calculator. Sometimes it writes it in different order. I don't care. If it's a calculator one, you want to do the derivative calculator, it's fine. But what you do have to do is write it down. All right, so you got 2 cosine 2x. What was it? Minus 2 sine x. Is that what it was? And then you have to put equals 0. You've got to do that. Okay? Now at this point, we're going to let the calculator solve this. All right? So back to our calculator. So now we're going to do a solve. We're going to go grab that f prime, which is there. We're going to put equals 0, comma x. Stop right there, Carly. And so we put comma x. Now, if we hit enter right now, one of two things is going to happen. What's going to happen, possibly? We're going to get a lot of answers that are not going to be between 0 and pi, and we might get that 2 pi n stuff. We might get that 2 pi n stuff, and that's usually not good either. So, and sometimes when you get a lot of answers, you get mad, you just throw your calculator right down the ground. So, we talked the other day about limiting it to 0 to pi, right? So let's do that. So we need to arrow outside of the parentheses. We need to get the vertical bar. Remember, the comma x goes in the parentheses. The vertical bar goes out. We're going to go less than or equal to, whoops, you did a vertical bar instead of less than. So less than or equal to, and then less than or equal to pi. And hit enter. Now you might want to hit control enter because sometimes when you're using a calculator, it's almost better to have decimals. You know, it doesn't really matter at this point. I think on this one, if you hit control enter or just hit enter, it gives you decimals either way. Okay, now there is that little warning, which means more solutions may exist. You know, right now we're going to kind of ignore that. But, you know, there may come a time where we got to kind of think about what it means there. But for right now, we're going to we're going to be good right now. So I'm going to write those two down. So we need to go to our paper and write those two down. So x equals 0.523. You don't have to round properly. That doesn't matter. 2.618 is what you would get if you round it, but if you just put 17 there, that's fine. Now, it turns out those are actual nice pi values. Does anybody know what they are? 0.523. I suppose that is pi over 6. It's pi over 6, and it's 5 pi over 6 is actually what those are. But it doesn't matter, right? Just use those decimals. Okay, so we just answered the first question. Are there any stationary points? We just found, right? And that's what we would write. X equals 0.523 and x equals 2.618. Those would be our stationary points. Okay? And we've shown how we got them. We did the derivative. We set it equal to 0. But we let the calculator solve it for us, which is fun. Okay, Jacob Roland, what's the next question? Where is f decreasing? So what do we do for that? When f prime's negative, so let's do a number line. Let's do a number line. So we're going to take these things now. Again, put f prime, label this number line. Because I believe here in a little bit, we're going to do an f double prime number line. Okay? So I'm going to put 0.523 on here. I'm going to put 2.618 on here. And now I've got 3 intervals in between all of them. So now I'm going to pick some numbers. And I need to keep them between 0 and 2 pi. So I'm going to put 5. I could put 0.5. Excuse me. I could put 0 there. But I'll put 1. I'll put 3. Okay, those are the ones I'm going to do. 0.5, 1, and 3. Now I need to do what with those numbers? Put them into, well, careful, f prime. Now that is going to be an issue for us, isn't it? Now that we have a list of candidates, sometimes we plug into the original, sometimes we plug into f prime. So we got to think about what it is we want. When we plug into the original, we're looking for the highest and lowest y value of the function. That's a global max min thing. That's not what we want. We want to know when f prime is negative. So we want to plug into f prime these numbers. Now, here's how I'm going to show you to do this on the calculator. There are a couple of cool little things we can do. The long way would be to now take, we're plugging them into f prime, which is this guy right here, right? Everybody see that? So we could just go 2 cosine 2 times 0.5 minus 2 times sine 0.5, and we could do that for each one of them. That's the long way. The not quite so long way, Carly, go up and grab that f prime. This is not the shortest way, but this is the next shortest way. Do the vertical bar. Because what we can do is, the vertical bar means with or such that. Now, if this gets confusing for you, if you feel you're not good with technology and all this stuff, just plug them in one at a time and just do that. Graph f prime and trace, whatever. There's a lot of ways on your calculator to plug a number into a function. You don't have to do it what I'm showing you here. I'm just showing you some options. So right now, we can write, there's our f prime with x's. Now we can do the vertical bar and now hit x equals 0.5. So what this is telling us is we want to do this function with x equals 0.5, and it plugs it in for us. And what are we looking at with that number right there? The fact that it's positive. That's all we care about. Okay, so we put a little positive on our number line. And now you want to arrow up, grab that thing again, and now all you have to do is delete the 0.5 and put a 1. Oh, whoops. So we hit Control Enter, because we want to know if it's positive or negative. And look at that, it's negative. And then we'll arrow up again, change the 1 to a 3, hit Control Enter, because we learned our lesson last time, maybe. And then we get a positive, and there we go. Now, let's go back to the cat. Before we talk about what the number line gives us, let's go back to the calculator. Let me show you an even cooler, shorter way to do it. I don't know about cooler, but it's shorter. So arrow up there and grab that derivative there again. Yep, grab that. And now erase the 3. We can actually plug all 3 in at the same time. We can let x equal a list. And the way we do a list is the curly brackets, which is above the right parenthesis. And now she can put 0.5, comma, 1, comma, 3, hit Control Enter, and it will return a list of all 3 values. So it's a pretty slick way to put 3 things into a function. You just put the function. Now, what some of you are going to confuse is you're going to try this, but you're going to put solve in front of it or something, right? Notice there's no solve in front of it. When we solved the equation, that was one thing. What we're doing now is evaluating an expression. So we put the expression, vertical bar, and what we want to plug into the expression. Those are 2 different things. So there would not be a solve in front of this when we're doing it. Some people think when they plug a 2 in and work it out, they're solving something. You're not. You're evaluating. Right? When you solve it, that's an equation that you solve. So it's important you understand that difference. So anyway, you see positive, negative, positive. All right. What they want to know when f is decreasing, well, there it is right there between those 2. And so you use your interval notation to get that answer. All right, what's the next question? Jacob Roller. Is that global max min or local max min? It just says maximum, right? So which one is it? It's global. Think about how they said it. What are the maximum and minimum values of the function? That's global. So they don't always use the word global. Sometimes they use the word absolute, and sometimes they word it just like that. Local, they'll usually say the word local or relative. Okay, these are global. So before we do that, let me not leave this real quick. So in this problem, they never did ask for local max min, right? But isn't it there? Don't we have everything we need for local max min? Right? It's all there, so if they ask us, we would have it, right? The number line, it's all there. All right, now they want global max min. What do we do for that? List of candidates. So over here, we have our list of candidates, which is our stationary points, which is when the derivative is 0, which we already know those points. And what else? The endpoints. And we need to plug those into the original. So we really have, because of the earlier work we've done, we have everything we need. So we need to get f of 0, plug in a 0. We need f of pi. We need f of 0.523. And we need f of 2.618. So we need to plug those into the original. Now we're going to go back to the calculator here in a second. But a word of caution. In science class, if they ever talk to you about having an issue if you take a number that's rounded and plug that then into a calculation, and that error gets magnified, right? So in other words, if you round to 3 decimal places and plug that in now to f, your answer may not be correct to 3 decimal places. So that's a problem. So I would suggest whenever you have a rounded value, now it's okay to just write 3 decimal places here. And when we give our stationary point answers, 3 is fine. But when we go to plug these into the function, we better plug 5 or 6 decimal places in. Luckily, those are all on the screen still. Okay? So we're going to go up here, or Carly is, and she's going to go up and grab the f function. Remember we typed it in originally? That's why we did. So she's going to scroll way back up there. She's going to grab the f function, the original, and paste it down. She's going to do her vertical bar. And what the heck, we might as well plug the whole list of candidates in right now in once. Right? So we can go vertical bar, x equals the curly brackets, whoops, curly brackets, there you go. Have to be curly brackets for a list. And we're going to plug in a 0 and a pi. And then, what was the point? We might have to scroll up to find this one. We better scroll up. There it was. You should probably want to jot this down. 523598. Okay, Carly, go. I think I got it. 523598. 523598. 523598. Okay, next one. 2.617. 994. Okay? If you go at least 6 decimal places, you should be safe. So what we're doing now is we're plugging those 4 things into our original function f. Okay, hit enter. And there we go. We got 2. We got -2. We got 2.598. Did I see that right? And negative 2 point, or did I have those backwards? Is that right? Okay. So therefore, where's my max? Or I should say, what is my max? 2.598, right? The y value is what I care about. And the minimum is that one. And so what I would do is just circle those. I would write the word max out there. I think if you do this, that's fine. You have your list of candidates. The biggest y value is the max, the littlest y value is the minimum, because we're comparing them. And that's our global max and min. Okay? All right. Is there more? There's one last thing, I think. Concave up. See, this is a good product because this covers everything we need to do. Now, I'm going to back up. Let me just show you something here. You don't have to jot this down or anything, but I'll show you this again on Monday. But I just made a little comparison here of chart stuff versus global max min. Now, we're doing it all in this problem, but global max min, we want to check the stationary points and the endpoints, which is when the derivative is 0. And we want to plug that into a list of candidates, plug it back into the original, find our max and min, which in this case would be the highest and the lowest point. A local max, a chart problem, is going to be number lines. Depending if we want inflection points, it's second derivative. If we want local max and mins, increasing, decreasing, it's first derivative. Set it equal to 0, do your number line. All your information from the chart is on that number line. Okay? All right. So, they want to do inflection points, or no, they say concave up, right? So we need the second derivative and set it equal to 0. Now, and we want to know when it's positive, right? So we need to set it equal to 0, do a number line, that'll tell us when it's positive. So let's talk about the calculator a little bit. So we need the second derivative, Carly. So what are we going to do? Okay, time out. Too fast. Delete that. We got two choices for second derivative. Okay, go back to that again. We got two choices. Right here. Delete that. Don't hit enter. Thank you. Stop. We got two choices. We can do the derivative of f prime, or this one here, the one that's got the little 2 on it, we can do the second derivative of the original, just for fun, because we haven't done that yet. Let's do that. So arrow over to this one. Grab it. See the little 2's there? That just means second derivative. Put an X down there. Arrow up there. Arrow into the box. Arrow into the box. Now go way up and get which one? Get which one? The first one, F. So we're going to have to go all the way up and get the first one, which is that one. There you go. Hit enter. Paste it in. There is your second derivative. Okay? Or you could have just done the derivative of the derivative. Either way. All right. So we get negative 4 sine 2x. And what was it? Plus or minus? Minus 2 cosine x. All right, and whoops, and we're going to set that equal to 0. You've got to have that on your paper. Even though the calculator did it for you, you've got to write out that equation. That's what you're solving. Now we can let the calculator solve it, so let's do that. So go ahead and solve that. We're going to remember we're going to want to solve it between 0 and pi again, so we're going to want comma x. We're going to want the vertical bar outside the parentheses. And pi halves is our one answer. Right? Or one. Last block we got the decimal 1.57 for that, which is interesting. I mean, it's the same thing, obviously, but I'm surprised it gave us pi halves. That's interesting. Okay, so there it is. So we now do our number line. So this is our possible inflection point, right? When the second derivative is 0, that is a possible inflection point. And so we're going to put it onto here, and we're going to pick some number. Now, this is like 1.57, so I'm going to pick 1. I'm going to pick 2 on either side. Now, normally I wouldn't do that if I was plugging into a trig thing. If I was doing it without a calculator, I'd want something nice with pi that I could plug in. But since we're using the calculator, it doesn't matter. So let's go ahead and grab that second derivative. And let's do the vertical bar, and we want to plug in a 1, and we want to plug in a 2, right? Something on both sides of pi halves. Oops, you got to have an equal sign in there. X equals the brackets. There you go. And control enter. When you see that, you know, whoops. Okay, negative and a positive, right? Negative and a positive. So all we were doing there is letting that plug in for us. All right. So this is concave up from pi halves to pi, right? To pi, not to infinity, right? Because we're going from 0 to pi is our unit. So from pi halves to pi, this function is concave up. Did it ask for inflection points? No, but is there one? Yeah. Since f double prime switches from negative to positive, f switches from concave down to concave up, so therefore the pi halves would be the inflection point if they ask that. Okay, 44 has it all in there. I don't know on the quiz that I would ask you one that has all that stuff, but 39 was supposed to be that, have all that stuff in it. Chart and global stuff, but no calculus. And so for tomorrow, you've got like 41 and 45, which 45 is just like this one. So give you a chance to try this from scratch yourself. All right, so that is, I'm going to give you the rest of the time to work. So you've got the next group of 3, 2, 5, 2, 6, 2, 7. So each of these assignments is kind of like a little quiz review in itself. Right? A little bit of the differential equation stuff, a little bit of the chart, a little bit of the global max min, a little practice with doing derivatives and well, not so much, well, a little bit of anti-derivatives maybe in there. Those are the things that the quiz is about next time. Oh, I forgot. We also have a little 5-point assignment, not bonus, but just 5 out of 5. This is your grade report. You would take this home and get this signed. Bring it back to me on Monday. We'll get 100%. Chris? Give it to your mother. Parents, yeah.
Well, like
I don't know why it's I suppose it's kind of notification Yeah, nice try. You said I usually hang on to this, just so you know. There was one time, I'd never forget this. It was one of the first years I was teaching calculus. I was sitting at the parent teacher conferences. I said, oh, you know, I sent home that progress report, and you know, at that time they looked at me like, wow, that guy right. That's the days before Power School, and you know, they could check the grade. I said, well, I sent home a progress report, and you know, at that time he said, well, we never signed a progress report. And so I dug out. I happened to have it, so I dug it out and I showed it to him. Oh, that's not our signature. So I think I got him in a little trouble. Didn't mean to. So anyway. Nope.